This lesson is on more gas laws. So, all of the gas laws that we've done so far all come from our ideal gas law, PV equals nRT. So Charles' law, Boyle's law, Gay-Lussac's law, they were uncovered before the ideal gas law. But now that we have this, we can get all of the other laws from this law. So what we're going to do is we're going to put all the variables on the left of the equal sign, and we'll keep the constant, or ideal gas constant R, on the right. So all we have to do is divide this side by n, divide this side by n, divide this side by t, divide this side by t. Cancels, cancels. So we end up with PV over NT equals R. Just a little bit of algebra there. So if we have one set of conditions, we can call that our P1, V1, N1, and T1. If we have another set of conditions, a P2, V2 over N2, T2, well, that also has to equal our ideal gas constant R. So we can say that by substitution, that P1, V1 over N1, T1 equals P2, V2 over N2, T2. And this is the form of the ideal gas law that we're going to use today to see how Boyle's, Charles, and Gay-Lussac's laws can be derived from that, and to get other gas laws as well. So if we just have some gas in a container and it's not undergoing a chemical reaction and it's not changing conditions, then we would just use PV equals nRT. But if we have changing conditions, then we want to use this form. Okay, so I've written that down 3 times here. And so first we're going to look at the circumstance where we don't have any moles getting into or out of our container and we keep the temperature the same. So N and T are constant. No moles getting in or out, the temperature stays the same. So if that is true, then we can say that N1 equals N2, and we can say that T1 equals T2. If it stays constant, whatever the temperature starts out as, it has to end up as. Same with the moles. So over here, if N1 equals N2, say this is 2 moles, that would be 2 moles, multiply both sides by 2 and it cancels out. So since they're the same, N1 cancels out N2. Since the temperature is the same no matter what it is, we're going to be able to cancel that out. So we end up with P1 V1 equals P2 V2. We just got Boyle's law. All we had to do was figure out what's not changing, and then we cross it out. So if we have a different type of problem where the pressure and N are constant, so no moles getting in or out of the container, and the pressure stays the same, then we can say that N1 equals N2 and P1 equals P2. So over here, if they're the same, I can cancel them out. And P1 cancels out P2. I'm left with V1 over T1 equals V2 over T2. Charles's law. And if I have a constant volume, a rigid container, a tank, or some other type of container where the volume is very, where it's sturdy and it won't expand, so if V and N, no moles again getting in or out, V and N are constant, then I can say that N1 equals N2 and V1 equals V2. If they stay the same, algebraically they cancel out, cancel them out, and I'm left with P1 over T1 equals P2 over T2, and we've seen this. That is Gay-Lussac's law. So starting with the ideal gas law, we can get each of our laws. So if you forget, do you multiply or divide? All you have to do is go back to the ideal gas law, cancel out what's constant, and see what you have left. And we know that when we have P1 V1 equal P2 V2, that's an inverse relationship. And here V1 over T1 equals V2 over T2, and the same with Gay-Lussac's, that's a direct relationship. So here if pressure goes up, volume goes down. If temperature goes up, volume goes up. And if temperature goes up, pressure goes up. Okay, so let's look at some more laws. So we can have the situation where the only factor that stays constant is N. So N is constant, meaning no moles getting into or out of the container. But pressure, volume, and temperature can all change. So that means that N1 equals N2, cancel it out, and we're left with P1 V1 over T1 equals P2 V2, sorry about that, P2 V2 over T2. The name of this law is the combined gas law. Again, you don't have to memorize that. As long as you have a problem and you have changing conditions and the moles don't change, cancel them out, and you end up with your law. Okay, so now, in every single law that we've done, Boyle's, Charles, Gay-Lussac's, and the combined gas law, the number of moles don't change. Well, what about if the moles do change? What about if you add some more gas or take some gas away? Then what happens? Okay, so we're going to look at the case where pressure and, what do I want to say, pressure and temperature are constant. All right, so that means that the volume can change and the number of moles can change. So that means that P1 equals P2 and T1 equals T2. If they stay the same, algebraically, we can cancel them out. So P1 cancels out P2 and T1 cancels out T2. So we get V1 over N1 equals V2 over N2. So this is a restatement of Avogadro's law of Avogadro. All right, so imagine you have a balloon and you blow it up a little bit. So you have a certain volume, you have a certain number of moles. Well, if you blow into it some more, your balloon gets bigger. The more moles of gas you put in your balloon, the greater the volume gets. So it tells us that we have a direct relationship between moles and volume. The more moles, the more volume. Okay, so let's see what we should do next. So now, next we could look at when we have V and T constant. So now the volume, so we're going to have some kind of tank or rigid container that's not going to change, and we're going to keep our temperature the same. So of course that means that V1 equals V2 and T1 equals T2. Cancel it out, V, T, T. And we end up with P1 over N1 equals P2 over N2. And we're going to see that this applies to Dalton's law. So again, we have a direct relationship between pressure and number of moles. So we imagine our container. We've got our gas in it. The particles are moving around. When we heat it up, if the volume stays the same, the particles move faster. They hit the sides of the container faster. Ooh, we're keeping the temperature the same. Okay, we've got our particles. They're at a temperature. They're moving around. If we add more gas, we've got more particles hitting the sides of the container. The pressure goes up. So we have the same temperature, but if the moles go up, the pressure goes up. All right, and now what about if pressure and volume are constant? So P1 equals P2 and V1 equals V2. Cancel out the pressure, cancel out the volume. We get 1 over N1T1 equals 1 over N2T2. So we can take the reciprocal of each side and we still maintain the equality. So that gives us that N1T1 equals N2T2. And there's no name for that. So this is telling us that when pressure and volume are constant, that the number of moles and the temperature are inversely proportional. So as your moles increase, the temperature has to decrease to maintain the same pressure. Because if temperature goes up and you're in the same volume, pressure goes up. To get the pressure to be the same, you have to remove some gas. So that is another relationship. So all of these all come from the ideal gas law. And you don't have to memorize any of the names of the laws. All you need to be able to do, figure out what factor is not changing and cross it out. Okay, so let's look at this problem. The pressure of 2.5 moles of gas in a rigid container is 770 millimeters of mercury. 5.6 moles of gas are added. What is the new pressure if temperature is constant? So we have changing conditions here. So we know that PV equals nRT. Get R by itself, divide both sides by N and T. And we get that PV over NT equals R. So P1 V1 over N1 T1 equals P2 V2 over N2 T2. So now we're going to cross out anything that is the same. It says temperature is constant. So T1 equals T2. Cancel it out. The pressure of 2.5 moles of gas in a rigid container, this rigid is telling us the volume doesn't change. So V1 equals V2. Cancel it out. So now we're left with P1 over N1 equals P2 over N2. We didn't have to memorize any law. All we needed was our good old ideal gas law. All right, so our P1 is 770 millimeters of mercury, and our N1 is 2.5 moles, equals. We're looking for the new pressure, we're looking for P2. Now, N2 is the total moles at that pressure. So our N2 is equal to the 2.5 plus the 5.6 that we added. All right, so that gives us, let's see, an 11, so 8.1 moles. So now we can cross multiply, so we get 770, I think I had a decimal point there, millimeters of mercury, times 8.1 equals 2.5 times P2. So divide by 2.5, and this is moles and moles, the unit cancels. All right, so let's see what we get. 770 times 8.1 divided by 2.5 equals. All right, so our P2 is equal to, let's see, I'm going to write this down and then we'll look at sig figs. 2494.8, our unit is millimeters of mercury. Looking at sig figs, we have 3 there because of the decimal point. We have 2 there, so we have to write this with 2 sig figs showing the magnitude of the number. So P2 equals, we got to round up here, 2500 millimeters of mercury. So because we added more gas, the pressure went up from 770 to 2500. Oops, I went off the page. There we go. 2500 millimeters of mercury. All right, so we'll do one more problem. And again, we're just going to figure out what law to use from the ideal gas law. All right, the volume of some neon gas at STP is 52.7 liters. What is the volume when the temperature is raised to 24 degrees C and the pressure is increased to 1.5 atmospheres? So we have changing conditions here. So we're going to use our P1V1 over N1T1 equals P2V2 over N2T2. All right, let's see what's changing. So the volume at STP, so remember this gives us a temperature and a pressure, is 52.7 liters. What is the volume? All right, so we're given, this is our V1, and we're looking for a V2. When the temperature is raised to, so this is our T2, and the pressure is increased to, and this is our P2. Our T1 is the STP temperature, and our P1 is the STP pressure. So there's no gas getting in or out, but pressure, volume, and temperature are changing. So the only thing staying the same is N. So N is constant, meaning N1 equals N2, so we can cancel it out. So we're left with P1V1 over T1 equals P2V2 over T2. And that is the combined gas law, but we didn't need to know that. All we had to do was cancel out anything that stays the same. And now we can go ahead and substitute into our equation. All right, so our P1 is the STP pressure, so by definition that is 1 atmosphere with, unlimited sig figs. Our V1 is given to us as 52.7 liters. Our T1 is the STP temperature, that is defined as 0 degrees C, which is 273 Kelvin. In all the gas laws, no matter what, you must use Kelvin for temperature. Equals P2, our pressure, or P2 is 1.5 atmospheres. We're looking for our new volume. We're looking for V2. And our T2, got to add 273 to that. 4 and 3 is 7, 9, 2. So we get 297 Kelvin. Okay, so now we need to do that algebra, and there's different ways to do it, whatever algebraic method you like, that's fine. I'm just going to cross multiply after I count out my units. So atmosphere cancels atmosphere, Kelvin cancels Kelvin, so now we cross multiply. So 1 times 52.7 times 297 equals, cross multiply, 273 times 1.5 times V2. Now I have to isolate my variable, get V2 by itself, so divide this side by 273 and 1.5. That means I have to divide this side by 273 and 1.5. This cancels, I get V2 by itself. My unit is liters because all the other units cancel out. And let's see what our calculator tells us. 52.7 times 297 divided by 273 divided by 1.5 equals, let's see, 3 sig figs, 38.2 liters is my new volume. Okay, so just remember good old PV equals nRT and go from there.